Okay, believe it or not, this is the third time that I've done this, so I'm going to try to get this finished before I have to leave here. So here we go. Ways we've already looked at stoichiometry. Basically, anytime we can get into out and out of moles, we've been doing stoichiometry. So grams to moles or moles to grams, we can use molar mass. We've already know that. Liters of solution to moles or moles to liters of solution. We use molarity to do that. So we're talking about this idea of that STP issue. So we know that PV equals nRT gives us this information that we can get moles, but in PV equals nRT, we only have one single pressure, volume, temperature. So that produces a little bit of a problem, but because we can solve for moles, we can get some information, excuse me. So we basically can do mole ratios after we have numbers of moles. The problem is that this 22.4 idea is at STP. And so anytime we're not at STP, we have to get into STP to be able to do the calculation with stoichiometry. If we're in STP, but we have other conditions, we've got to get out of STP and go to the new conditions. So to do stoichiometry, we have to be in STP. So the gas laws are going to come into play because we're going to need to be able to transfer from one state to the other. So STP versus non-STP. And I'm going to try to show you how we're going to do that. So we always, once we get to moles, we can do a mole ratio, we can get back out of moles. But the key here is the STP issue. So let's look at this problem. First of all, how many liters of carbon dioxide are produced if 2.67 grams of solid sodium bicarbonate are heated? So we see that we have a problem here. We have a pen. I'm going to put purple because I'm liking that color today. So we know that we have sodium bicarbonate, that's NaHCO3. And when I heat that above 80 degrees Celsius or so, I get Na2CO3 plus H2O plus CO2. I'm sorry, CO2. Water is H2O, right? Clearly I can see that the NAs are not balanced. Let me go ahead and balance that. I'm going to have 2 over here for the Na. That's 2 H's, so I've got 2 H's there. That's 2 C's. I've got 1 C there and 1 C there. That's 2 C's. I've got 6 O's, 3 O's, 1 O, 4 O's, plus 2, 6 O's. So now I'm balanced. You will notice that it doesn't say anything about STP. If it doesn't have any information, you're going to assume STP. If it gives you information, then you have to assume something differently. So here we go. So 2.76 grams of sodium bicarbonate, okay? We're going to change that to moles by 84.080 grams over 1 mole, right? Then we have moles of something, so now we can do the stoichiometric ratio, the mole ratio. We have 2 moles of the bicarbonate to 1 mole of carbon dioxide, so 1 mole of carbon dioxide goes on the top. 2 moles of the bicarbonate goes on the bottom. Okay, now we can change to liters because we have 22.4 liters in STP or 1 mole of CO2. Moles of CO2 are gone, moles of bicarbonate are gone, grams of bicarbonate are gone, and we get an answer, and the answer we get is 0.368 liters of CO2. And that's at STP because we have no other conditions to go by. Not too bad, right? So we're going to have to introduce a little problem here because remember, anytime we bubble things over water, we've got to start thinking about partial pressures because when we're bubbling things over water, that's going to give enough energy to the water molecules to then become vaporized. So we're going to be doing some of that and making sure we do that. So when we collect over water, we have a situation like this where we have something that's being bubbled in right here from a place, and it's being collected up here. The air is pushing down here on this water. The gas is pushing on this liquid in here, and this is representative of the vapor pressure of the water and the gas together. Notice that they're both pointing into that container. and this represents the pressure of the air. So how do we make sure that those two things get equal? Well, what we have to do is we have to make sure that the level of the water in both of the systems, the water that's being pushed down in the air and the water inside the tube, the collection tube, is the same. Once we do that, because the level of the water is equal, we can assume the pressure on the inside is equal to the pressure outside. We can make that assumption. So the pressure of the air is equal to the pressure of the gas and the water vapor. That's pretty important. So then we solve for the pressure of the gas. Pressure of water is temperature dependent. We've got the chart. Remember, we've got this chart right here. Somebody left this chart in class today, so if you've left your chart in your worksheet, it's in class and it's in the crate. But we've got this chart that has that information in kPa. So the barometric pressure is basically the pressure of the air. So if we find the barometric pressure, we can look that up on the weather station, and we can know a lot of information about the pressure of the air because of that. So we're going to be using that information. Okay, so here we go with the problem. We know that sodium metal is added to water, so when we do that, we know that we have Na plus H2O. And we know that when that happens, sodium dances on top of the water, but if the water is spiked with phenolphthalein, that we'll get a pink reaction or a pink liquid. So we know that we're making NaOH. And we're also making H2 gas. If we collected that, that would actually show up. So what we see here for our balancing, we see one Na, one Na, two H's. We have three H's. Not so good right there, right? Three H's. So I'm not going to change this 2H thing, but what if I put a 2 here? That means I need two NAs. Now I have two O's and one O, so I have to put a 2 here. 2 plus 2 times 2 is 4, so I have two H's here and two H's here. There's 4, so now I'm balanced. So I have 43.2 milliliters of hydrogen gas are produced at 767 torr and 59 degrees Celsius in excess water. How many grams of sodium are reacted? So the first thing that we have to do is we have to figure out this whole idea of the pressure and temperature. And the fact that we're in water, we now have to account for water that may also be within the gas. So the first thing I'm going to do is 676 divided by 760, or 767 divided by 760 is going to give me 1.01 atmospheres. Okay, that's important because that's the pressure of all of everything. But we know that we're at 59 degrees Celsius, and at 59 degrees Celsius, we know that 19.028 kPa is the vapor pressure of water. So if I divide that by 101.3 kPa, I'm going to get that that is 0.188 atmospheres. And that's the water. So if the water plus the hydrogen is equal to 101, then I have to subtract 0.188 from that, and I get 0.822 atmospheres. And this is the atmospheric pressure of the hydrogen gas. So that's where we need to start. Now, we're also at different conditions other than STP. So we have to do something a little bit more creative. So what I know is that according to the combined gas law, P1V1 over T1 is equal to P2V2 over T2. I'm going to be looking for V2. To look for V2, I've got to rearrange the equation. So V2 is equal to P1V1 T2 over T1 P2. Remember, these are my STP conditions right now because they're the ones that I'm going to. So I'm going to erase a few things. Okay, erase, 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 erase. I spend a lot of time erasing. Okay, I'm going to keep the formula right there because I want to make sure that I know what I'm doing. Because I want to find STP conditions. I can't do stoichiometry until I'm in STP because I don't have a way to go to liters of gas. So here we go. So I know these are my conditions right here that I need to solve for. I need to solve for V2. V2 is equal to P1, which was 822 atmospheres, A volume is 43.2 milliliters. T2 is the new condition, so that's the 273 Kelvin. I'm going to divide that by T1. T1 is this temperature. Remember, in Kelvin, it's 332 Kelvin. Times P1, remember, or I'm sorry, P2, P2, which is 1.00 atmospheres. I'm going to STP. All right, so atmospheres are going to go, Kelvin's going to go, leaving me with liters, and what I end up getting for V2 is I end up getting 29.20 milliliters. So that's where I'm going to start the next portion of my problem. So let me go ahead and erase again. Okay, I'm going to start the next portion of my problem with the 29.2. Okay, so here we go. So 0.0292 liters divided by 22.4 liters, because now I'm at STP. I know the moles of hydrogen now. Once I know the moles of hydrogen, I can use my mole ratio. Remember, I've got 1 to 2, so I have 2 moles of sodium to 1 mole of hydrogen. And now I want grams of sodium, so that's 22.99 grams of sodium over 1 mole of sodium. Sodium moles cancel out, moles of H2 cancel out, liters of H2 cancel out. And I'm going to end up getting an answer of 0.0599 grams of Na. So that's my answer there. Okay? So not too awfully bad. A little more complicated than you like, but you have to remember when we have gases, we always have to be in STP to do stoichiometry. If you're not in STP, you have to get to STP conditions before you can continue the problem. Okay, so let's see what's next. We also have to remember that if we're doing stoichiometry, everything is open in stoichiometry. Limiting reagents, excess reactants, theoretical yield, percent yield, using percent to find percent composition of an unknown, all of that stuff is open to play. So if we look at a problem, we see acetic acid reacting with sodium carbonate. So let's see, acetic acid is HC2H3O2 plus sodium carbonate is Na2CO3. Very similar to what we talked about in class today, but we have a different acid, so we're going to make Na, not H, C2H3O2 plus water plus carbon dioxide. Okay, so we need to balance it. We see we have 2 NAs, so I'm going to have to put a 2 here. Now I need 2 acetate, so I'm going to have to put a 2 here. I've got 2 hydrogens. I've got 1 CO3. I've got 1 C and 3 O's, so I'm good there. I'm now balanced. But you see, I have information about both of my reactants, which means I'm going to have to find which one is limiting. So I'm going to go ahead and start out with the 5 grams. So 5 grams of sodium bicarbonate, or sodium carbonate, not bicarbonate, sodium carbonate. And I'm going to take that and divide it by 105.99 grams and 1 mole. And I'm going to get that I'm going to need, or I have 0.042472 moles of the sodium carbonate. Okay, how much acetic acid do I need for that? Well, let's see. What's the stoichiometric ratio? I need 2 acid to 1 sodium carbonate. So 1 sodium carbonate goes on the bottom, 2 moles of acid go on the top, and I get that I'm going to need 0.0944 moles of the acid to completely react with all of that sodium carbonate. So now I have to go over here. How much acid do I have, in fact? So you can see I have molarity. So the first thing I'm going to do is I'm going to change to liters, 0.020 liters of acid times 1.5 moles of acid in 1 liter of acid. And I have 0.030 moles of acid Now, I could move on from here, but I really don't need to, because what I know is this is what I have, this is what I have, and this is what I need. I can see my need is much greater than what I have. So the acid must be the limiting reactant. So I know that this is the limiting reactant, so in reality, I don't need to know this anymore, okay? All of that makes no difference. So erase again. I'm gonna erase this stuff. It was important because I had to figure out what was limiting, but now I know it's limiting, I can go from there, okay? So, because I'm starting with liters of a solution, I've got this problem that I have right here. I know my moles of acid that I have, so let's go ahead and start right there. I want to go to volume of CO2, right? So I have moles of my acid. I'm going to do my mole ratio. Notice I have CO2 1 mole to 2 moles of acid. So I'm going to put 2 moles on the bottom of the acid, 1 mole of CO2. I want volume of CO2, so I'm going to use 22.4 liters. But remember, that's STP. We're still going to have to do something in just a moment. And that's going to give me that I have 0.336 liters. 0.336 liters. I want to double check my math just to make sure. Yep, 0.336 liters. So that's what I get for the number of liters. But remember, I'm not at STP conditions. I also have water that I'm probably bubbling through, so I have to take that into account when I'm doing this problem. So got to erase one more time. Okay, remember my answer. I'm going to leave that up there so that we have it. Okay. All right, so we go to the next portion of our problem. So now we've got to use our combined gas law to figure out the new volume that's not at STP. But before we can do that, we have to find the partial pressure of the gas. Look at the temperature. I'm at 23 degrees Celsius. So if I look on my sheet, I find what the vapor pressure is. I change it to atmospheres, and I get 0.0277 atmospheres. Okay, so now I want to take this amount minus this amount. So if I do that, I get that the carbon dioxide, sorry about that, I get that the carbon dioxide is 0.8503 atmospheres. How did I do that? 0.787 minus this number. Why? This was the pressure of everything. This is the pressure of water. So that's the pressure of the CO2. So now we can use V2 is equal to P1 V1 T2 over T1 P2. Be really careful here though, because we're in STP and we're going to something else. So P1 is 1.0 atmospheres. V1 is 0.336 liters. T2 is the new condition. T2 is 23 degrees Celsius, so that's 296 Kelvin. Okay. T1 is the condition we were at, that's STP, so that's 273 Kelvin. Times P2. P2 is right here. We just calculated that, 0.8503 atmospheres. Okay, so when we get that, I'm erasing our answer because we don't need that anymore. This is not the right answer for our problem at the moment. Okay, so when we get that and we calculate, we are going to get 0.428 liters, or 428 milliliters. So I know this looks complicated. It's not really as bad as you think it is. Many of you are going to be a little frustrated. But remember, the stoichiometry is the same. We just have to add the gas law component to it. Okay? So good job.